Doubly reinforced concrete beams use both tension and compression steel bars to resist heavy loading. Tension steel resists tensile forces and compression steel, along with concrete, resists compressive forces. In this tutorial, you will learn step-by-step process on designing doubly reinforced concrete beams. I will be solving 2 examples. Stay tuned until end of the tutorial to learn fully how to design these beams. If you have missed theoretical part of doubly reinforced concrete beams, click on this side of the screen to come on over. Hey friends, if you're new here, I am Dr. Jawed Qureshi, a senior lecturer in structural engineering and design at University of East London. On this channel, we explore civil engineering and human skills to help us lead more productive, happy, and examine life. A simply supported reinforced concrete beam is shown in figure 5. Both permanent and variable loading is as indicated. Assume cover to the reinforcement as 40 mm and FCK 25 Newton per millimeter square. FYK is 500 Newton per millimeter square. Now first, we have to calculate the moment of resistance for this reinforced concrete beam, and should this beam be designed as singly or doubly reinforced beam. So up to this position, you don't actually know if it should be designed as singly or doubly reinforced beam. So it will depend on moment of resistance. In my opinion, moment of resistance should be worked out really properly. If you work out moment of resistance correctly, then the chances are the rest of the question is just a recipe to solve the question. And in part B, determine the area of bending reinforcement required for the beam and suggest a suitable size and number of bars. Now here you're asked determine the area of bending reinforcement required, and with the help of a design sketch, show the location of reinforcement provided. Now this bending reinforcement can be tension reinforcement, it can be compression reinforcement. The span is 5 meter and GK and QK are given. B is 250 and H is 400. Now here H is given, D is not given, so we have to find out D. First thing first, you have to have a look at these design formula. First, you have to determine the moment of resistance. But for finding moment of resistance, we need to find out design load. Now, FCK is given to us, FYK is given to us, and cover to reinforcement is given. If cover is not given, simply assume it. And ultimate load, the factored load is 1.35 GK plus 1.5 QK. GK is 15 and QK is 30. So if you put these values, you will get value of W or design load as 65.25. And once you have this design load, then simply you can work out design moment. Now here W is worked out already, and L is the span, which is 5. And if you put it in the formula, you're getting MED as 204 kilonewton meter. Assuming bar dia to be 25 millimeter and height is 400 millimeter, height of the beam is overall depth of the beam is 400 millimeter, then the formula for depth is total height, take away cover, and take away half diameter of the main bar. This is giving me value of D as 348. Any question up to this point?
So what is D? D relating to your depth, did you say?
Yes, D is effective depth, which means that it is from the center of tension reinforcement to top of the beam. Then we have to find out the moment of resistance, and the formula for moment of resistance is, again, I will follow these steps. I will follow this recipe. MRD is equal to 0.167 FCK BD square. Now this is the reason I needed a value of D, because the formula does not use H, where H is overall depth of the section. 0.167 times FCK times B times D square. B is the width of the beam and FCK is the material strength or concrete compressive strength, and 348 is value of D, which I have just determined. Now remember that this is BD square. There's square on D. Now, when you get all these values, you are going to get value of MRD in Newton into millimeter. Don't forget to convert it into kilonewton into meter, because our applied moment is in kilonewton meter. So if you don't convert it, then you will get quite long value. So if your value is very long, it means that you have certainly made mistake somewhere along the lines. So if value is too long, then it means that there's some mistake. And then multiplying with 10 raised minus 6, it will give us this moment in kilonewtons. So moment of resistance of this beam is 126 and applied moment is 204. So when moment of resistance or capacity of the beam is less than applied, then we always design it as doubly reinforced beam. So have a look. When MRD is less than applied, then we design it as doubly reinforced beam. If MRD is greater than applied, then we design it as singly reinforced beam. Now, this is a very crucial stage in designing if it should be designed as singly or doubly reinforced beam. Yeah, go ahead.
Question: Why, if MRD is greater than MED,
Yes.
why do you even need? Why would you need to have a singly reinforced beam? I don't understand, because the
Yes.
beam efficiently
Yes.
strong.
MRD is the compression resistance of the beam. So MRD is related to something which is above neutral axis. Concrete will always need tension reinforcement, because below neutral axis, this is neutral axis, below neutral axis, this portion is not taking any tension at all.
Yeah.
Right? Yes, I accept that moment of resistance is sufficient, but that is sufficient in concrete part, in compression part. Not in concrete, in compression part. So compression part is the top part. So that is strong in compression part. Okay, it doesn't need any compression reinforcement. That is the meaning.
Yeah, I get
When it is strong in compression part, it doesn't need any compression reinforcement. But the portion which is below neutral axis, that is the tension portion. Tension strength of concrete is almost zero. It is 10% of its compressive strength. We ignore tension capacity of concrete. It means that whatever is below neutral axis is ignored. Then something should be there to take into account tension. And that's the reason we use singly reinforced beam in tension side. Did I answer your question?
Yeah, very clear, thanks. And so in all cases and all concrete beams, basically, you should always have tension reinforcement.
Yes, definitely. Definitely. You should always have tension reinforcement is compulsory. If there is no tension reinforcement, then the failure is going to be catastrophic. It's going to fail so suddenly without giving any warning, and it will fail very quickly. It will not take any load at all, even, because when you apply loading on a beam, it starts to fail on the tension side. And the tension strength of concrete itself, although it is 10% of its compressive strength, it means that if it is 25 Newton per millimeter square concrete, its tensile strength is going to be 2.5 Newton per millimeter square. But that's really very low strength for tension. And sometimes even it is less than 10% of its compressive strength. So it's always better to ignore the tensile strength of concrete. And in all these design calculations, tensile strength of concrete is ignored.
Thanks.
This actually determines that if we need compression reinforcement or not. Now we have determined that our MRD, moment of resistance, is less than applied moment. This means that we should do something about moment of resistance to increase its moment of resistance. There could be two ways. One way could be to increase the dimensions of the section. Sometimes due to architectural reasons, it is not possible. The other way could be that we use compression reinforcement and design it as doubly reinforced beam. So here we will design it as doubly reinforced beam. It means that the extra moment demand required is going to be met by compression reinforcements. So you have 204 minus 126. Now 78 kilonewton demand on moment, that has to be met by compression reinforcement. And you will see that, and this is the reason that you can see that it is MED minus MRD. It means that the remaining moment demand is to be met by compression reinforcement. This is the reason that it is MED minus MRD here in compression reinforcement. Assuming dia of bars to be 16 millimeter of compression bars, D2 is equal to cover plus phi dash divided by 2. D2 is from the center of compression bars to the top of the beam. So it would be concrete cover. Concrete cover is from the outside of the bar to the top plus half diameter of the compression bar. Cover is given 40. Diameter of compression bar we have assumed as 16. D2 is going to be 48 millimeter. Now D2 over X should be less than or equal to 0.38 according to this recipe formula. So D2 over X should be less than or equal to 0.38. D2 is 48 and value of X is equal to 0.45 D. So X is equal to 0.45 D. D we have just determined, and this is 0.31, which is less than 0.38. It means this is fine. And then we have to determine AS2. AS2 means compression reinforcement. Compression reinforcement means that ones that we provide at the top in a simply supported beam. Again, I'm using these values. AS2 is equal to MED minus MRD divided by 0.87 into FYK D minus D2, where MED is 204, MRD is 126, FYK is the yield strength of steel, and D we have determined earlier, that is the depth, effective depth 348, and D2 is the distance from center of compression reinforcement to the top fiber. When you put these values, now again you're putting MED and then MRD. Now difference is going to be 78. You have to convert this back into Newton to millimeter, because if you have a look at denominator, you can see that FYK is in Newton per millimeter square, D is in millimeter. All units should be consistent, otherwise you will have a mistake. Now once we have this AS2, this comes out to be 598. Our assumption was 16 millimeter dia bar. Then simply you will go to this table where you will see these values. So 16, so if we can use 3 number 16 bars and provide 603. Let's see what we have done. Yes, this is 598, and then we're just providing just above required area. So if you have a look at this table, this is telling you cross-sectional area of bars. If you're using number 16 and if you use 3 of them, the area is going to be 603 millimeters square. And this is what I have used over here. And on the right side, you can see marks given for each step. Again, marking scheme is going to be similar but not the same.
So you just tell me what D2 over X is again, please.
Yes. Now in this formula, D2 over X, it actually controls the location of neutral axis, and this ensures that your section is under reinforced. So there are 3 sections: balanced, under reinforced, and over reinforced. Controlling this value of D2 over X, we are actually ensuring that our section is under reinforced. And under reinforced is something which we want. It means that there's not much reinforcement than required. Now you will say that, okay, what are the implications? Implications are that if you have over reinforced section, then it will fail in a brittle manner and without giving warning. If you have under reinforced section, then it will fail in a ductile manner and it will give you warning. So by controlling this D2 over X value, we are actually controlling the position of neutral axis. If this comes out to be more than 0.38, because X is equal to 0.45 D, then we increase the depth of the beam so that we can control this value. Then we find out the tension reinforcement. And for tension reinforcement, first we have to find out this lever arm. For lever arm, K dash is equal to constant value 0.167. And then area of steel, we have this formula. Now K naught dash is equal to 0.167. And we put this into this formula, we get value of Z as 385. that is lever arm. Sorry, this is not 385. That's what I was thinking. How can it be more than Z? So this is not 385. This is 285. It has to be less than depth. So again, if you have a look at this formula for AS1, which is area of tension reinforcement, we have MRD divided by 0.87 FYK into Z. So Z we determine 285, not 385. And AS2 is the required area for compression, not provided. Once you put these values, then you have AS1 as 1614, and our assumption was that our main bar is 25, has 25. Again, I would go back to this table and see what is closer to this 1614. Okay, so 25 bars. So 1614, probably 4 bars 25 will give me 1960 millimeters square. That will do the job, I think. So 4H25 will do the job. It has to be more than what is required. Once you have done this, then provide a design sketch. So bottom reinforcement is 4H25. The compression reinforcement is 3H16. And if you are asked to design shear, then you can simply draw some stirrup here. And then D2 is 40 and D is 348. It's useful to provide a design sketch. Any question?
I have a question.
Yes, Marjan, please.
So when calculating D, this D value, we have to assume the diameter of a rebar.
Yes.
If it turns out we use a slightly larger diameter later on, do we have to recalculate the whole thing from the beginning?
No, I would say that simply slightly over designed. So for example, if the required is 1614, use slightly more. So that will take into account the effect of revising. I mean, it should actually be in theory revised, but if you slightly over design it, then leave a comment that you are slightly over designing it rather than revising it.
Yeah, I think that's reasonable.
Yes.
In the practice question, I think I used 8 millimeters for one of the compression part. Compression.
Yes, another note is that your assumption should be sensible. So for example, if you're assuming 8 millimeter for a stirrup, it makes sense. Normally we use that. For example, if you are saying that for compression, you're using 8 millimeter, so that's not very reasonable assumption. The reasonable assumption for tension bars are 20 and 25. And reasonable assumption for compression bar is normally 16. You could go to 12 as well, but 12 is not really good assumption. So compression 16 and tension 20 or 25. That is the reasonable assumption. So if you say that you are assuming the bar to be 6 millimeter dia, then it's not a reasonable assumption for tension bar. I know, I mean, you would not assume it. I'm just giving example.
Would it be reasonable to assume a larger diameter if the given UDL is quite large? I mean, larger than the ones in practice questions?
It will depend on the moment. If UDL is large and span is large, if you are having design moments more than 600, 700 kilonewton meter, like 1000 kilonewton meter, then by all means assume 32 millimeter. If the design moment is quite large means more than 700-800 kilonewton meter, then in that case you can assume it to be 32.
Thank you, that makes sense.
Any more questions?
No, I don't think so, sir. I think you've been very clear.
Okay. Then you have another similar question, but you have larger loads. I would suggest that you solve this question.
Can you please provide a solution for that one to check our answers with?
Actually, I'm not sure if I have solution for that. I mean, if you like, I can solve it, but I want you to have a go actually.
Yeah, I mean, like just posting the solution like next week or something.
Let's do it then. So we have 6 meter, we have GK equal to 20, QK equal to 40 kilonewton meter, and the section is 300 by 500, and FCK is 25 Newton per millimeter square, FYK is 500, I think, Newton per millimeter square. Okay, the first thing first is that we have to work out design load. So design load will be equal to 1.35 GK plus 1.5 QK. This is part A. So in part A, and 1.35 into 20 plus 1.5 into 40. So if you do calculations with me, just give me the answer.
87.
87. Thank you. Kilonewton into meter. Design moment MED. MED is equal to WL square over 8. W is 87. L is 6.
391.5.
391.5 kilonewton meter. And the next step is to find out MRD, all right? Ultimate moment of resistance. MRD 0.167 FCK BD square. But first we need to find out BD square. Concrete cover is given to us as well. So D will be equal to H minus C minus P over 2. H is 500. C is cover, which is 40. And assuming the bar dia to be probably 20 or 25. 20 divided by 2, that will be 450, is it?
Yep.
450 millimeter. Now we have to find out ultimate moment of resistance. Ultimate moment of resistance is MRD. MRD is equal to 0.167 FCK B and D square. So 0.167 FCK is 25, B is 300, D is 500 times 10 raised minus 6.
253.6.
253.6
53.6.
kilonewton meter. That's MRD. Should it be designed as singly or doubly reinforced beam?
Doubly.
Because this is less than MED. Okay, MED is 395. So doubly reinforced beam. Okay, design it as doubly reinforced beam. Now for doubly reinforced beam, what you need is, first of all, you need to verify D2 over X should be less than 0.38. So I have to determine D2 as well. D2 should be equal to cover plus phi dash divided by 2. So cover is 40 plus phi dash, assuming it to be 16. So this will give me 48 millimeter. So D2 over X should be less than or equal to 0.38. D2 is 48 divided by X is 0.45 into D. D is 450. Should be less than or equal to 0.38. So let us see 0.237. So this is okay. The next step is, are you following me?
Yep.
Yes.
The step is area of compression steel, AS2. Now area of compression steel, MED minus MRD divided by 0.87 FYK, D minus D2. MED is 391.5, take away 253.6, 0.87 into FYK is 500 into D is 450 minus D2 is 48, and this has to be converted into Newton into millimeter. All right, so that's why I multiplied it with 10 raised 6. I'm getting 785.7, so 786. Are you getting this as well or not?
I had a different diameter assumption. I had 25 millimeter assumption, so I get 805 millimeters squared.
All right, okay, that's fine.
I'm getting the same as you, Joe.
No problem. Area of compression steel is there. Then after that, I have to find out Z. Lever arm. K dash is equal to K naught dash is equal to 0.167, where Z is equal to D 0.5 plus under root 0.25 minus 3 K naught dash divided by 3.4. So Z is 450 into bracket 0.5 plus 0.25 minus 3 into K naught is 167 divided by 3.4. I'm getting 369. Are you getting, if your diameter is 20 and if you're getting this, then it should be okay. Or if you're getting a different value, then I may have made a mistake. But I think it looks sensible.
I've got the same.
Wonderful.
Yes, 368 millimeters.
368, yes, not much different. And then area of tension steel. Actually, I should have provided the compression bars, but I will do it a little later. Area of tension steel. So AS1 is equal to MRD divided by 0.87 FYKZ plus AS2. MRD was 253.6 and 0.87 times 500 times 369 plus AS2 is 786. I'm getting 2366. Actually, I should have used 25 millimeter bar. So let's see what happens. Margin seems to be correct. So let's see.
2380. Not much of a difference.
Not much of a difference actually. Yeah. Let's first of all find out the compression one. So for compression, let us use 4 H16 bars. This will give us 804. Use 4 H16 bar. AS will be equal to 804. So from here we can see that 804 millimeter square for 4 bars of the 16. 2366 AS1 area is quite high. That means that I will have to use 8 of H20 bars. So 8 of them does not make much sense to me actually.
So when you see that you might need more than 5 bars, would you reconsider diameter?
Yes, definitely. My assumption was 20 and your assumption was 25. Let us use 5 25 bars. It will slightly over design it. That will be good actually. So how much required area are you getting, Marjan? AS1?
2380, considering 25 millimeters diameter.
All right. So it means that the slight over design will do. So it means when I'm assuming 20 millimeter and I'm getting 2366, so I can slightly over design it by 5% or so. Because with 20 mm diameter, I will have to provide 8 bars. So 8 bars are too much. I won't be able to fit in properly. That's why I will use 25 millimeter 5 bars. If I revise my calculations, which I think Marjan has done for me, she's getting AS1 to be 2380, isn't it?
Yes, 2380. Just
So it's not
a small difference.
Yeah, huge difference. So slight over design will do the job. I would say use 5H25 and AS1 will be equal to 2450 millimeter, and you can put a note saying that slight over design will help us not to repeat calculation for different or diameter.
Thanks for watching. Don't forget to subscribe for more practical insights into structural engineering and beyond. Until next time, stay curious.